Hello everyone, and welcome back to another calculus video. In this video, we are going to explore the idea of sequences. So when we talk about a sequence, we're talking about a list of numbers that are following some kind of pattern. And we're really going to focus on infinite sequences, and that's going to lead us to the idea of infinite series later. So we could think about writing the sequence. Notice the notation here, the curly brackets and then a sub n. So that subscript is the index variable of the sequence, and it will identify what term you're on. So if we have a sub n as an infinite sequence, we could think about a1 would be the first term, a sub 2 is second term, and so on. Each of those numbers are called terms, and we can usually think about them in terms of formulas. And we could write that formula for that sequence using function notation. When we talk about an arithmetic sequence, we're talking about a sequence where we're adding things constantly. Geometric sequences are a little bit different. We're thinking about raising something to a power here. So let's look at a few examples. For each of the following sequences, let's find an explicit formula for the nth term of the sequence. So we have negative 1/2, 2/3, negative 3/4, 4/5, negative 5/6. Let's figure out if we have some kind of pattern that we can see with this. So notice we're alternating from positive terms to negative terms. So I could think about negative 1 to the n, and I'm thinking about starting where n equals 1. So if n is 1, I'm going to get a negative term. If n is 2, so this term would correspond to n equals 2, I would have negative 1 squared, which would be a positive term, and then a negative, and then a positive, and a negative. So that negative 1 to the n is going to give me that alternating pattern that I'm looking at. And then now we want to figure out how can we write all of these terms in terms of that n. So I'm going to label these. That negative 1/2 is happening when n equals 1. That 2/3 is happening when n equals 2. That negative 3/4 is when n equals 3. 4/5 is when n equals 4. Negative 5/6 is when n equals 5. So you can see that the number of the term corresponds with what's in the numerator, so we could call that n. And that denominator is whatever the next number is, so we can use n plus 1 to show that. So our sequence can be written as negative 1 to the n times n over n plus 1. Let's see if we can figure out something with that next one. So I'm going to identify each one. 3/4 corresponds to n equals 1. 9 over 7 corresponds to n equals 2. 27 over 10 is n equals 3. 81 over 13 is n equals 4. And that next one, 243 over 16 is n equals 5. So everything in the numerator looks like it's multiples of n. So this looks like it's 3 to the first. This is 3 to the second. This is 3 to the third. This is 3 to the fourth. And this is 3 to the fifth. So we've got 3 to the n in the numerator. We just have to figure out how to write that denominator. So we have a difference of 3 for each of these. So when n is 1, then my number is going to be 4. The output is 4. I'll call it y. And when n is equal to 2, my output is 7. So I see that this is a linear pattern. Let's see if we could figure out what that equation would be between there. We could find the slope, since we identify that it's linear. Slope is y2 minus y1 over x2 minus x1. And then we can use my y minus y1 equals slope times x, which I'm using n's for x's, x minus x1. So we have y minus 4 equals the slope of 3 times n minus 1, using that first point there. So we have 3n minus 3, so y equals 3n plus 1. And I always like to test it and make sure that that's going to work. So when n is 1, I'm going to have 3 to the first over 3 plus 1, which is 4. When n is 2, 3 squared is 9 over 6 plus 1, which is 7. When n is 3, 3 cubed is 27 over 9 plus 1, which is 10. So you can see how that's giving me that pattern. So we're pulling in a lot of different things that we're thinking about that we've learned, like identifying linear functions and finding the equation between 2 points for that one. Let's look at the next example. For each of the following recursively defined sequences, find an explicit formula for the sequence. So let's write out a few terms, and we're looking for patterns here. So they're telling us A1 is 2, and all the other terms is going to be A sub n equals negative 3 times A sub n minus 1. So A sub 2 would be negative 3 times A sub 1, which would be negative 3 times 2, which is 6. A sub 3 would be negative 3 times A sub 2, which is negative 3 times negative 3 times 2. So look, I've got negative 3 times negative 3. That's negative 3 squared times 2. Let's look at A sub 4. So it's going to be negative 3 times A sub 3. So it's going to be negative 3 times my A sub 3. So that's negative 3 squared times 2. Okay, I noticed I didn't multiply that out. A lot of times you don't want to go that far because it's easier to see the patterns if you leave the terms multiplied together. So that's why I scribbled out that negative 6. It didn't really help us in that next step. So now I have negative 3 times negative 3 squared, which is negative 3 cubed times 2. So you can see the pattern happening here. This guy, going back up to A sub 1, would be negative 3 to the 0 times 2. And then I have negative 3 to the first times 2. So my pattern here, A sub n, would be negative 3 to the n minus 1 times 2. Let's look at that next one. We have A sub 1 equals 1/2. And then my formula is A sub n equals A sub n minus 1 plus 1/2 to the n. And that's going to work as long as n is greater than or equal to 2. And they're giving us that starting point as 1/2. So A sub 2 is going to be A sub n minus 1, which would be A sub 1 plus 1/2 squared. So I'm going to have A sub 1, which is 1/2, plus 1/2 squared. So I'm going to leave it like that for now. Let's write out a few more and see if we need to go tweak that. So this is A sub 3 is going to be A sub 2 plus 1/2 cubed. Let's go ahead and multiply that out. So we have 1/2 plus 1/4. So that's 3 over 4. A sub 2 was 3 over 4, and we're adding 1/2 cubed, which is 1/8. So 3/4 plus 1/8 is 7 over 8. And then A sub 4 is going to be A sub 3 plus 1/2 to the 4th. So A sub 3 is 7 over 8 plus 1 over 16. And that's going to be 15 over 16. So let's see if we can see some kind of pattern here. So the denominator, when n is 1, I have 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So that's 2 to the n. The numerator, so I see 2 to the n minus 1 here. Let's see if that works. So if n is 4, 2 to the fourth is 16, minus 1 is 15. If n is 3, 2 cubed minus 1 would be 8 minus 1, which is 7. This would be 2 squared minus 1, which is 3. And this would be 2 to the first minus 1, which is 1. So that matches my numerator. And we could leave it like that, or we could split that numerator and think about it as 1 minus 1 over 2 to the n. Either one of those would be perfectly fine. And sometimes it takes just looking at it and trying different things to see if you can figure out what that pattern's going to be. Given a sequence a sub n, if the terms a sub n become arbitrarily close to a finite number as n becomes large, we say that that sequence is converging to L, and the limit of the sequence is going to go to L. So now we're going to start talking about taking the limit of a sequence. We want to know if it's going to converge or if it's going to diverge. It diverges if it doesn't go to a specific place. In this case, they're calling that place L. So we're approaching a finite number. So we're taking limits at infinity again. So notice as we're going to positive infinity, when we talk about sequences, we usually start with n equals 1, and we're using whole numbers to get there. So let's look at a few and determine whether or not we have a divergent or a convergent sequence. So if we look at this one, part A, we have the sequence 5 minus 3 over n squared. We want to take the limit as n goes to infinity of that sequence, 5 minus 3 over n squared. So as n gets larger and larger, that fraction is getting smaller and smaller. So this guy is approaching 5. So we say this is convergent and that limit is 5. If we look at that next one, we're taking the limit as n goes to infinity of 3n to the fourth minus 7n squared plus 5 over 6 minus 4n to the fourth. So this is in the form infinity over infinity. So we could use L'Hopital's rule here. We could take the limit as n goes to infinity, take the derivative of the top, which would be 12n cubed minus 14n, and the limit of the bottom is negative 16n cubed. That one is again infinity over infinity. And we can just keep doing that. Take the limit as n goes to infinity. 36n squared minus 14 over 16 times 3 is 48. So negative 48n squared. Again, that's infinity over infinity. So 36 times 2 is 72 n over negative 96 n. Now you can see those n's are going to reduce, and that limit's going to go to negative 72 over 96. And that guy reduces to negative 3 over 4. So that limit is negative 3 over 4. Okay, we could have also thought about this as a function, and we're taking the limit of a rational function as n goes to infinity. Well, it's going to be what that horizontal asymptote would be. The degree of the top and the bottom are the same, so this is going to go to negative 3/4. So let's look at C. I'm going to write C up here. We're going to take the limit as n goes to infinity of 2 to the n over n squared. So the top's going to infinity and the bottom's going to infinity, so we would use L'Hopital's. The derivative of 2 to the n is 2 to the n ln of 2. Derivative of the bottom is 2n. Again, that's infinity over infinity. So we're going to take the limit as n goes to infinity again. The derivative of the top is going to be ln of 2 times 2 to the n times the ln of 2 over 2. And you can see that that numerator is just not going to get any smaller. So this guy is going to head to infinity. So this is a divergent sequence, because those terms are getting larger and larger and larger as n gets larger and larger. That's different than the other ones because they were heading to a specific place. The terms were heading in that first case to 5, in the second case to -3/4. And then let's look at D. I'm going to take the limit as n goes to infinity, 1 plus 4 over n to the n. So if we were to think about infinity, this is going to 0, so I have 1 to the infinity. And remember our trick to solve that. We are going to rewrite this as y equals the limit as n goes to infinity of 1 plus 4 over n to the n. And we're going to take the ln of both sides. Our goal is to be able to apply L'Hopital's. Oh, I forgot to write my ln then. Then I'm now going to rewrite this. So this is the limit as n goes to infinity. Oops. Sorry about that. I mean that n to be in there. So let me recap what I did. So I rewrote the limit as y equals. I'm taking the ln of both sides. The reason I do that is so I can bring that exponent down. Now the limit of the ln is the ln of the limit, so I could write that in any order. That n does have to stay inside of the limit. We have not taken the limit yet. Now we have to write this in the form that we can apply L'Hopital's. Right now we can't apply L'Hopital's. So this is going to be the ln of 1 plus 4 over n. And I could rewrite that multiplied by n as 1 over n. And now as n gets larger and larger, I'm approaching the ln of 1, which is 0 in the top, and the bottom is also approaching 0. So now I'm in the form of 0 over 0. So let's apply L'Hopital's rule. So take the limit as n goes to infinity. So I need du over u. So let me write some stuff over here. I have the ln of 1 plus 4n to the -1. And that's what I want to take the derivative of. So the derivative of that inside is going to be -4n to the -2 over 1 plus 4n to the -1. And then I'm going to simplify that. So we have -4 over -4 over n squared over 1 plus 4 over n. So let's insert that. So that's the derivative of my top, -4 over n squared over 1 plus 4 over n, divided by, and then the derivative of the bottom. This is n to the -1, so it would be negative n to the -2. And then we need to clean this up. Let me fix my notation there, make that 4 a little clearer. So I have limit as n goes to infinity, this is negative 4 over n squared over 1 plus 4 over n, and we are dividing by the denominator, which is negative 1 over n squared. When we divide fractions, we do keep, change, flip. So I have negative 4 over n squared over 1 plus 4 over n times negative n squared over 1. And then when we multiply those fractions across, we're going to have a 4 over 1 plus 4 over n. That's what we're going to take the limit of as n goes to 0. Sorry, as n goes to infinity. That 4 over n is going to go to 0, so this is going to go to 4 over 1 plus 0, which is really just a 4. Now remember, we said that was equal to the ln of y. So the ln of y is equal to 4, which means e to the 4 is equal to y. So that sequence, so therefore, the sequence 1 plus 4 over n to the n is going to converge to e to the 4th. Sometimes we'll need to apply something called the squeeze theorem to a sequence to figure out what's happening. So let's say we've got 3 sequences, A sub n, B sub n, and C sub n. And there's a place where B sub n lives between A sub n and C sub n. If we know that A sub n and C sub n both go to a same place, we'll call it L, then it's going to force this B sub n to go to L also, because those values live between the other 2 sequences. So it's kind of squeezing B between 2 things that we know. Let's look at a couple of examples of where we could use that squeeze theorem. Let's say we want to look at cosine of n over n squared. So we know something about cosine of n. We know that the cosine function is always going to be between negative 1 and 1, so it lives there. So if we divide everything in that statement we know by n squared, then we can apply that squeeze theorem. We're talking about n values like 1, 2, 3, 4, and so on. So these n's are getting larger and larger. So if cosine of n lives between negative 1 and 1, then the cosine of n over n squared has to live between negative 1 over n squared and 1 over n squared. Well, what do we know about negative 1 over n squared and n squared? We know that the limit as n approaches infinity of negative 1 over n squared, those values are heading to 0. And we know that the limit as n goes to infinity of 1 over n squared is also going to 0. So if this is going to 0 and this is going to 0, then this guy has no choice. It has to go to 0. So cosine of n over n squared must also go to 0 by the squeeze theorem. Let's look at that next one. We have negative 1/2 raised to the nth power. We want to know what's happening to that guy. So give me just a second. I'm going to move all of this information over just a little bit so I have more room to write. So B. So let's see what we can think about this guy. Would you agree that this is an alternating sequence? If n is positive, if n is 1, I'm going to get negative. If n is 2, it's going to get positive. N is odd, it's going to give me a negative. N is even, it's going to give me a positive. So let's see if we can wedge this between a negative sequence and a positive sequence. So negative 1 over 2 to the n is going to produce negative values. 1 over 2 to the n is going to produce positive values. These values will live between those two sequences. So if we look at the limit as n goes to infinity of negative 1 over 2 to the n, as n gets larger and larger, that whole fraction is shrinking to 0. Same thing is going to be true for the limit as n goes to infinity of 1 over 2 to the n. That's going to head to 0. So then we can conclude that negative 1 over 2 to the n has to go to 0 also. So I'm plotting this in Excel so you can kind of see what's going on. So here's my n, okay? This is a sequence we started with, negative 1/2 to the n. So if I plug in n is 1, I'm going to get negative 1/2. If I plug in n is 2, I'm going to get positive 0.25 or positive 1/4. 3 is going to give me a negative, 4 is going to give me a positive, and so on. So this was my lower bound. So in the negative 1 over 2 to the n. So when I made my statement here, okay, these are all the negatives, and these are all the positives. So the negatives and the positives. So this column, you can see that this lives between these two values. And that's a less than or equal to statement here. And that's perfectly fine. You can see how my values are bouncing back and forth there. And so when I plot everything, I've got this blue sequence of those negative values. And then I've got this sequence of the positive, the ones that's bouncing back and forth. And then that green is the positive. And some of my dots are getting overtaken by the other colors, but you can see how it lives in between these values. It actually lives on top of one or the other, but everything is converging towards 0 for the value for that sequence at n. And that's what we're looking at there, the value of the sequence, and that's what the squeeze theorem is doing. Let me draw the other one too, just so you can see that. We talked about cosine of n over n squared. So I'm going to have a column for n's, and I compared that to negative 1 over n squared. Let me change this to text. So format cells, text. So this is negative 1 over n squared. This would be cosine of n over n squared. And this is going to be 1 over n squared. So I'm starting with 1, increasing, and I'll just do a few of these, maybe go up to 10, 12, something like that. So this is going to be negative 1 divided by n squared. This is going to be positive 1 divided by n. Oops. Got my equals. Divided by n squared. And this is going to be equal to cosine of n divided by n squared. So you can see how this value lives between that lower bound and that upper bound for all of these. Let me see if it'll let me graph this. Insert scatter plot. I mean, you can really see it on this one. Those orange dots live between the green dots and the blue dots, the blue being the lower bound, the green being the upper bound. So that's what the squeeze theorem's doing, is it's squeezing this between two things that we know. Now, we can't use the squeeze theorem always, but these are good examples where we can. So we can talk about boundedness. A sequence is bounded above if there exists a real number m such that all the sequence values are less than whatever that number m is. We're bounded below if all the sequence values are larger than our below bound. They're calling that M again. And if it's not bounded, so it just keeps going to positive infinity or negative infinity, then we would say we have an unbounded sequence. If we have something that converges, it's always going to be a bounded sequence. And then we could talk about what monotone means. A monotone sequence is one that is increasing or staying the same, or decreasing or staying the same. So everything's doing one thing. It's either always going up or it's always going down. If we were to look at these examples here, I'm going to go back to my Excel spreadsheet. This is not monotonic because I am bouncing back and forth between positives and negatives. Same thing here, this is not monotonic. Okay, but if I look at this right-hand side, this guy would be monotonic because it is always decreasing. Same thing here, this would be monotonic also because it's always going in that same direction towards 0. We could say this guy's bounded above and below. Okay, 0 is, I'm approaching 0, so 0 would be my lower bound, and the biggest thing I could get out of that 1/2 to the n would be 1/2, so it's bounded above as well.